Hello everyone! Today we'll be learning about unit conversions. So it's a very math heavy process, but I think it's really important, especially in the field of horticulture. I mean, fertilizer calculations are a huge part of growing, especially in greenhouses. And greenhouses don't always have internet, so you can't always just go onto some of those calculators and figure it out. So it's nice to know the basis as well as be able to get out of a few ordinary niche problems from day-to-day life. So this is applicable for a lot of different fields, and it's also extremely well used in chemistry. So let's get going. First, the bones of any unit conversion problem are how you set it up. There's two options and none of them are right or wrong, but this is what I call the fraction setup. So it's basically just fractions, anything like that. And then our other option are train tracks. So our numbers and letters go up here. So again, no specific reason, whatever makes you happy. I know some people really don't like fractions, so this might give them trauma or something. So the train tracks method is good for you. I'll be trying to use train tracks for this video just because it's usually a little neater, but I am someone that uses these fractions, so I might slip up. So what you populate your framework with, for the most part, are something we call conversion factors. So these are any type of relationship of equality between two units. So for example, 12 eggs per 1 dozen. This is a true fact, and you have to make sure that you're always right. So if you're doing a conversion that you're not sure about, please look it up, because if your conversion isn't correct, like if you accidentally say 13 eggs per 1 dozen, that could mess up your whole problem. So another example could be 1 dozen eggs per 1 crate in a truck, and then we've got 20 crates per 1 truck. These are all true statements, but you can't really look up this. This is something you'd probably be given in your word problem or package directions or something like that. So you notice that I've made these diagonal, and this is on purpose. What we want to do is we want to make sure that our units are, first of all, we always write our units. That's really important, both for yourself and for whoever is grading your work. But we want to make sure that all of our units cross out. So dozen and dozen, these are diagonal. We've got crates and crates, diagonal. And whatever doesn't have diagonal pairs is going to end up in the end answer. So we've got 12 times 20, which is 240, I think. Eggs is that top. And then the bottom would be 1 truck. So this is your first conversion problem. This is 240 eggs per 1 truck if you were given all of these conversion factors and you already knew 12 eggs per dozen. So you might be wondering, or it might be hard to remember, why units always go diagonal. And my favorite example is algebra. So if you've got 3x times, say, 3x. You know that to find this, you're going to be crossing out this, right? Because as you go through this, we've got 1 over 3x times 3x. These cross out, and they get just 1. So another way to think of this is geometry. If we've got a square, and we've got 2 feet by 2 feet, to find the area, we multiply 2 feet by 2 feet, right? And our answer is 4, but our units are feet squared because we've not only multiplied 2 by 2, we've also multiplied feet by feet. So for example, if we set this up wrong, and I'll do a shortened version, we'll say 12 eggs per 1 dozen, oops, times 1 crate per 1 dozen. Then we've got this issue where, okay, we're multiplying these, so we get 12. And we multiply these, so we get 12 egg crates. Oops. Times 1 dozen by 1 dozen, so that's 1 dozen squared, and that obviously doesn't make sense. So if you end up with an answer like this, where we're multiplying things and we get really weird units that aren't the case, that's a really good indication that you should go back and make sure that you have everything crossed out. Because again, if something's not crossed out, it's gonna end up in your end answer. And finally, let's talk about more how I've been finding these answers. So let's do another example problem. Let's say I have 14 ounces of pudding per 1 pudding cup. I've got 48 cups of pudding in 1 box. Each box weighs 45 kilograms. Again, this is just arbitrary. These probably don't exist. That's a very heavy pudding. And then we say for every 100 kilograms, you get $50 for your pudding. So these are just arbitrary unit conversions. I gave them to you so you can say, oh, these are true. It's the same as a word problem. And we wanted to make sure that we start crossing things out first. 1 cup, cup, box, box, kilograms, kilograms. So what we're left is ounces and dollars. So now we're going to be finding how many ounces are in $1. So if we pay $1, how many ounces of pudding do we get? I'm not going to belabor the point of dollars being in the front, but just know it's whatever unit. So even if your unit's at the front, it's still a unit. So there are 2 main ways to do these problems. The first is to multiply everything in the top row and then divide everything in the bottom row. So if you're got your calculator out, you'll be putting in 14 times 48 times 1 times 100. And then you're going to the bottom row. And when I say divide everything by the bottom row, I don't mean multiply everything together and then divide. I mean divided by 1, divided by 1, divided by 45, divided by 50. And then you'll get your answer. However, the second option usually works best for people that use this fraction method. It just works better in their head. So people that use the fraction method often go ahead and do 14 divided by 1 times 48 divided by 1 times 1 divided by 45 times 100 divided by 50. So if you put this into the calculator either way, it should come up with the same answer no matter what. And again, so it's just whatever makes most sense to you, but you just want to make sure your top row is always going to be preceded by multiplication and your bottom row is always going to be preceded by a division. And with that, you should be able to do whatever you want with unit conversions. So I'm going to go ahead and do one more example. So let's put all of this together and let's say that we have 5 cups in 1 box. And each box weighs 5 pounds. I get $15 for each pound of cups. What we're gonna do is 5 times 1 times 1 divided by 1 divided by 5 divided by 15. And we wanna make sure that our units cross out. So we're left with cups again, dollar at the bottom. Do a quick calculation because I didn't think of this equation ahead of time. 5 divided by 5 divided by 15. It will equal 0.067 cups per dollar. So when I pay $1, I will get 0.067 cups. All right, so what I'm gonna do is I'm going to put a few question problems in front of the screen, and you can pause and do them if you want, and I will put the answers at the end of the video. Okay, so the big question here is why we need unit conversions for fertilizer calculations. And there's a lot of answers there. However, the main issue is that fertilizer requirements for individual plants are typically in parts per million, ppm, or field requirements are in, say, pounds per acre or kilograms per hectare. Excuse me. So when you want to buy fertilizer, it's reported in convoluted percentages that basically force you to do math to figure out how much you need to give your plants or field what they have been required based on these specific units. So let's start with the easier aspect there, and it's reported fertilizer requirements. These are found in scientific papers, general recommendations, and results from soil tests. For example, you read that your tomato plant needs 300 parts per million nitrogen, or you tested your 5.2 acre blackberry field and they tell you you need 30 pounds of phosphorus per acre. Just a few examples of many, but whatever you're told, you go and buy that fertilizer for those specific amounts. So when you get to the fertilizer store or wherever you're getting fertilizer, you'll find on the bag 3 numbers like this. So it could be like 10, 10, 10 or 20, 0, 3. Any 3 numbers on your bag. These are what's in the bag. In the industry, we call these NPK usually, like, hey, what was that NPK reading, etc. And that means that the first number is nitrogen. The second number is phosphorus. And the third number is potassium. So NPK are just the elemental letters. Like if you look at your periodic table, you'll see these correlation. It is kind of hard to remember phosphorus and potassium because they both start with P, but potassium is K. And if you look at a periodic table, that can help you remember. So when we have this percentage, that means that this bag is 10% nitrogen, 10% phosphorus, 10% potassium. If you have, like I said, 2003, it's 20% nitrogen, 0% phosphorus, 3% potassium. So whatever remaining percentage, by the way, like 23, what's the other 67%? That's just what we call inert material. It could be dye, certain bulky material to help spreading easier. Anything that's aside from that is just a different aspect of the fertilizer to help it, but it's not an actual nutrient, or it could be different micronutrients. However, the terrible and convoluted thing about these percentages is that they're not actually nitrogen, phosphorus, potassium. I know we call them NPK, but it's actually not the case at all. So someone decided a long time ago that they would report these percentages instead of NPK. It's still nitrogen. Don't worry about that. But our phosphorus is actually reported in phosphate, PO4, 3, something like that. And then potash, which is KOH. So that's a real problem because if you're thinking about these molecules, we've got, yes, potassium in here, but what do we do with this O and H that are also contributing to this molecule? So that's where we're starting to get some issues, is that what do you do, right? Like we're just reporting, this isn't actually 10% phosphorus, it's 10% phosphate. And that's where the unit conversions come in. We have to figure out how to get to this reported value of phosphate to phosphorus, because again, that's what we're getting reported in. Someone said spread 30 pounds of phosphorus on your farm, not 30 pounds of phosphate. So let's do an example with nitrogen just to get used to doing fertilizer equations, and then we'll move on to these harder ones. So let's say we still have our 10-10 bag of fertilizer, and we have a soil report that tells us we need 40 pounds of nitrogen on our 1 acre field. Well, again, we're going to be looking for how much nitrogen in a fertilizer we need. Excuse me. So what we're going to do is we're going to say, okay, we have 40 pounds, or excuse me, handy little whiteout here. So we don't have 40 pounds. Our unit we want to match is just pounds of nitrogen. So we start with the only things that we know, which are that we've got 40 pounds of nitrogen for one field that we need, and our fertilizer is 10% nitrogen. Remember, we don't have to worry about this, so we can just take that at face value. Now, so what we have here is pounds of fertilizer, right? Fertilizer. So again, this is our fertilizer. It's 10% nitrogen. So whatever pounds of nitrogen we have, the whole is fertilizer. So 10% can be written a few different ways. You could either say 0.1 nitrogen to 1 fertilizer. You could also say 10 pounds nitrogen to 100 pounds fertilizer. It doesn't really matter as long as you're true to the percentage. Like you could even say 10 pounds to 200 pounds. It doesn't matter as long as you keep the percentage accurate. So for now, let's just say 0.1 pounds nitrogen to 1 pound fertilizer. And that's pretty much it, right? So we have pounds nitrogen crossed off. And so we're left with how many pounds of fertilizer per our acre field. Simple as that. So what we do is we 40 times 1 divided by 1 divided by 0.1, which I believe is 400, but let me check here. It is, I was right. So 400 pounds of fertilizer are what we need for this specific 10-10-10 fertilizer to accomplish this requirement. So hopefully that makes sense. All right, now let's make this a little more complicated and start thinking about these two troublemakers here. So let's say that instead of nitrogen, our soil report said we need 40 pounds of phosphorus for our 1 acre field. Now we can still go ahead and say that we have 0.1 phosphate for our 1 pound there, 1 pound of fertilizer. And then we just need one more conversion factor, and that's something that is incredibly hard to find online for some reason. So I'm gonna try to give it to you on the screen here so you can take a screenshot or anything. And so knowing that, we can just go ahead and say that 1 pound of phosphate is equal to 0.44 pounds of phosphorus. And then we just go ahead and make sure we've got pound of phosphorus, field remains, pound of fertilizer remains, phosphate. And then we go 40 times 1 times 1 divided by 1 divided by 0.1 divided by 0.44, which would be, let's just say 400 divided by 0.44 equals, so we'd need 909 pounds of fertilizer for this one field. Hopefully that all makes sense. So let's do another practice question to tie things up and talk about parts per million, because I mentioned that before and it's super easy to deal with, but let's just do an example problem to make sure it works in everyone's head here. All right, so what we want to specifically talk about now for our example is parts per million. So anytime you see ppm, it equals parts per million. And you can always, whenever you see that, you can immediately turn that into milligrams per liter. And this is a lot easier to work with because we've got our unit conversion here already. You don't have just this one number floating around. You already have broken it down into the solid and liquid state. Liter usually refers to 1 liter of water, but not always. But in the realm of fertilizer equations, 1 liter is always going to be water. So say you get 200 ppm. That is just 200 milligrams of your fertilizer in 1 liter of water. If I can draw today. So let's do a basic equation with this. So let's say we've got that 300 parts per million. Let's just go ahead and start with nitrogen for now. So let's say a tomato plant needs 300 parts per million nitrogen. And we've got our 30, 20, 0 fertilizer. So these are the 2 things we're given, but this is a lot of information that we can work with. So first we're going to go ahead and turn this immediately into milligrams of N to 1 liter of water. Our nitrogen in this fertilizer is 30%. So again, we can just say 30 milligrams N per every 100 milligrams. I'm just going to shorten this to fert. So this is just our 30. Remember, you can also do 0.3 over 1. I just wanted to show you that you can do it both ways. And so if we go ahead and continue here, we're going to cross out these. And then all we're going to be left with is how many milligrams of fertilizer we need. So that'll be 1 liter of water. It's always 1 liter of water. Get my trusty phone out here. And it'll be 300 times 100 divided by 30. So we'll need 1,000 milligrams of fertilizer, which is also just 1 gram. And as promised, here are the answers to those example questions. Hope you learned a little something, and if not, I'm sure your teacher will be able to clarify anything that you need. Have a good day.